Let us continue periodic properties. In the periodic properties, first one is atomic radius. Atomic radius definition will take the nucleus of an atom. Nucleus of an atom we will take it is sphere, and outermost boundary of an atom we will take. Outermost boundary of an atom. We are taking outermost boundary of an atom. Okay, nucleus of an atom and outermost boundary of an atom we have taken. Here we will take center of nucleus. Center of nucleus. Next, outermost boundary we will take this distance. This distance is called atomic radius. So atomic radius means distance between center of nucleus to outermost boundary. That is called atomic radius. But describing outermost boundary is difficult. It is not possible. And also isolating an atom and nucleus center to outermost boundary, practically it is not possible. So finding atomic radius is individually. Finding atomic radius by isolating an atom is difficult. So what is the other ways to find atomic radius? That we will see. The other ways are what, in the sense, one is called by taking metal lattice. By taking metal lattice, we can find a radius. We can find. So what is lattice? That we will see. What is lattice? Lattice is called a three-dimensional arrangement of constituent particles. Three-dimensional arrangement of constituent particles is called atomic radius. Three-dimensional arrangement of constituent particles is called lattice. Okay, so lattice means three-dimensional arrangement of constituent particles. Here constituent particles are what means metal atoms. Metal atoms are constituent particles. So how the metal atoms arranged in a metal lattice, that we will see. How the metal atoms arranged in a metal lattice, that point we will see. This is a one metal atom. This is a another metal atom. This is a next metal atom. This is a next metal atom, and so on. It continues like this. So in the metal lattice, metal atoms arranged like this. Now we will see here in this metal atom center point we will take. In this metal atom center point we will take. In this metal atom center point we will take. This distance we will consider. This distance is called a internuclear axis, internuclear distance. Internuclear distance we can see. So you are taking metal lattice in the sense three-dimensional arrangement of metal atoms. So this is one metal atom, it is the neighboring metal atom. These two metal atoms are just in contact with each other. In this metal atom center point we are taking, in this metal atom center point we are taking. Now from this center to this center, this distance is called a internuclear distance. In this internuclear distance, you take off, divide this by 2, that is called what means crystal radius. That is called crystal radius. Crystal, what is meant by crystal? Crystal in the sense three-dimensional regular arrangement. Three-dimensional regular arrangement of constituent particles is called crystal. Now in this crystal we have found radius, therefore it is called what means crystal radius, we can say. Okay, so crystal radius in the sense you have to take internuclear distance, in that off you have to take, that is called a crystal radius, we can say. So what is meant by crystal radius, that we got an idea. Now crystal radius, for example we will take a example for this one. Example is sodium. We will take sodium is a crystal. We are taking sodium. This sodium we will take. Now internuclear distance for sodium is how much, in the sense 3.72 angstrom. Therefore crystal radius of sodium. So crystal radius of sodium is how much, in the sense 1.86 angstrom. So internuclear distance of sodium is 3.72 angstrom. So crystal radius of sodium is how much, in the sense 1.86 angstrom. This is for metals we can find like this. For non-metals, what to do? For non-metals, in the sense, for non-metals, for gases, these and all, what to do? Sir, for example, we'll take chlorine gas. We'll take chlorine gas. In the chlorine gas, what is there? Chlorine gas consists of chlorine molecules. Chlorine gas consists of chlorine molecules, you can say. Chlorine molecules are coming under which type, in the sense diatomic. In the chlorine molecule, what type of bond is there? Means covalent bond is there. Covalent bond is there. In chlorine molecules, covalent bond is there. Sir, now we will take one chlorine molecule. We will take one chlorine molecule. We will take. Okay. Now we will consider chlorine molecule. So one chlorine atom, another chlorine atom combining to give chlorine molecule. It is one chlorine atom, it is another chlorine atom combining to give chlorine molecule. For this chlorine atom, we will write electronic configuration, that is neon 3s2 3p5. Neon 3s2 3p5. 3s2 in the sense the s orbital contains 2 electrons. 3p5 in the sense the 3p contains 3 orbitals. The 5 electrons will distribute 1, here 2, here 3, here 4, here 5. So 5 electrons we distributed. This is one electron. This one electron is called unpaired electron. This unpaired electron present in which this unpaired electron present in this p orbital. This unpaired electron we will consider for chlorine. So chlorine nucleus we will consider. Then chlorine unpaired electron present in this p orbital. That p orbital we will consider like this. So that p orbital we consider. In this p orbital, this unpaired electron we will consider. We are considering unpaired electron. Okay, so this unpaired electron we have considered. Next we will take this chlorine. For this chlorine also same electronic configuration. So we will consider nucleus of chlorine. We have considered nucleus of chlorine. Then we will consider this p orbital. This p orbital, unpaired electron present in the p orbital we will consider. So p orbital is called a dumbbell shape. That dumbbell shape we considered. That dumbbell shape contains what, in the sense unpaired electron. This unpaired electron we will consider. Now what will happen means this chlorine atom is containing this 3pz unpaired electron. This chlorine atom is containing this 3pz unpaired electron. Now both chlorine atoms come together and form chlorine molecule. That means these two 3pz orbitals come closer and forming molecule. So how that molecule will be there, we'll see. It is one 3pz orbital. It is another 3pz orbital. Both are overlapping here. That means interpenetrating here. This electron cloud and this electron cloud partially interpenetrating, partially overlapping here. That is called a bond. That is called what we can say bond. It is nucleus of one chlorine atom. It is nucleus of another chlorine atom. Here both the electron clouds of chlorine atoms are overlapping with each other. Therefore, here what is formed, in the sense bond is formed. This bond is called a covalent bond. This is a chlorine molecule. This is chlorine molecule. So in this chlorine molecule, what we have to do means, here center of nucleus we have to take. This center of nucleus we have to take. This distance is called what, in the sense bond length. This distance is called what, in the sense bond length. In this bond length we have to take off. That off is called what, means covalent radius. This is called what, in the sense covalent radius, we can say. So we got covalent radius here. Now we got covalent radius of which one, in the sense chlorine. We got covalent radius of chlorine, we got it. Sorry. So what is the value of a covalent radius of chlorine? That we will see. Chlorine covalent radius we will see. Chlorine, this bond length is 1.98 angstrom, and the covalent radius is how much, in the sense 0.99 angstrom. Covalent radius of chlorine is how much, in the sense 0.99 angstrom, and the bond length is how much, in the sense 1.98 angstrom. Sorry, this is about covalent radius of chlorine. Sorry. Now we will compare atomic radius and covalent radius. These two values we will compare. Now we have to compare. We want to compare atomic radius and covalent radius. These two will compare it. These two values will compare it. Now we will take hydrogen atom. Hydrogen atom we will take. For hydrogen atom, nucleus we will consider it is a nucleus, and hydrogen atom is having 1s1 electronic configuration. S is called spherical shape and symmetric. That 1s1 electronic configuration we have given. It is for one hydrogen atom. Now we will say atomic radius. Atomic radius we will say it is the center of nucleus. It is the outermost boundary. This distance is called what means atomic radius. That distance is called atomic radius of what means hydrogen atom cell. So for hydrogen atom we got atomic radius cell. Next we will see covalent radius of hydrogen. Covalent radius of hydrogen, for which hydrogen molecule will take, it is hydrogen molecule. Hydrogen molecule is formed by hydrogen atoms. So hydrogen atoms combine to give hydrogen molecule like this. Now one hydrogen atom will take, in one hydrogen atom nucleus is like this, and 1s1 electronic configuration we are writing. It is 1s1 electronic configuration. It is another hydrogen atom nucleus. It is 1s1 electronic configuration of hydrogen. 1s1 electronic configuration of hydrogen. Now these two hydrogen atoms combine to give hydrogen molecule. That means its 1s1 electron cloud and its 1s1 electron cloud come closer and meet each other and interpenetrating with each other partially. That is called overlapping. Due to that overlapping, a bond is formed. Okay, so this electron cloud and this electron cloud come closer and interpenetrate to each other to partial extent. Interpenetrate to each other to partial extent. So this electron cloud is coming here, this electron cloud is here, both electron clouds are being here, they are overlapping with each other, interpenetrating. Now this nucleus we will write here and this nucleus we will write here. Now this overlapping is called bonding. That bond is called covalent bond. Therefore covalent bond is formed. Now we will see the radius. We will see. Now here this center of nucleus, this center of nucleus will take, this is called what in the sense of bond length. This is called a bond length. In this bond length you take off, that is called what means covalent radius of hydrogen. Covalent radius of hydrogen. So covalent radius of hydrogen is how much in the sense from here, this center point, this center point, this center point, this is called covalent radius. This is called what means covalent radius. Now you see what is atomic radius and what is covalent radius. You see atomic radius means center of nucleus to outermost boundary surface, that is atomic radius. Covalent radius means center of nucleus to the in this overlapping part of we have to take, that distance is called covalent radius. Now let us compare this atomic radius and covalent radius, whether they are equal or not. You see how the magnitudes are there, means atomic radius is greater than covalent radius. Atomic radius is greater than covalent radius. Like this is the atomic radius and covalent radius we have compared. Next we will compare atomic radius and crystal radius. We will compare atomic radius and crystal radius we want to compare. Okay, so atomic radius, then crystal radius. This another name is called metallic radius. Crystal radius also called what means metallic radius we can say. Now atomic radius will take, here nucleus will take, atom is a sphere, atom is spherical, therefore we have taken like this. Now we will consider a center of nucleus. Center of nucleus we will consider, and outermost boundary we will consider. This distance is called what in the sense atomic radius. That distance is called atomic radius we can say. Next we will see crystal radius. We will see. Now we will consider crystal. Crystal means metal lattice. Now one metal atom we will consider like this. Next another metal atom we will consider like this. Another metal atom. Next metal atom we will consider like this. Next metal atom. Next metal atom we will consider like this, and so on. Metal atoms we consider like this. Next we will see center of this metal atom. We will take center of this metal atom. Then center of this metal atom we will take. This distance we will take. It is called the internuclear distance. In this distance half we will take, that is called a crystal radius. That is called a crystal radius or metallic radius. So this half in the sense how much that we will see. Off in the sense this center of nucleus will take, and here will take. It off means this much. Off means this much. Okay. So this is called what in the sense crystal radius. It is called crystal radius. So how the atomic radius and crystal radius are there on comparison? Compare these two. Atomic radius and crystal radius compare. How it is there means atomic radius is nearly equal to crystal radius. Atomic radius is nearly equal to crystal radius, like this is there. Set. Next type of radius. Next we have seen like this. Set. So we can find crystal radius for what in the sense for metals we can find crystal radius. Covalent radius we can find for covalent molecules. Covalent molecules we can find covalent radius. What about noble gases? Noble gases helium, neon, argon, these are all not forming any compounds. They are not metals, they are gas. Therefore, how to find radius for that? How to find radius for that? That we will see. Now, we will take this argon. Argon in a solid state we will take. Argon in solid state we will take. Okay, we are taking argon in solid state. So, argon in solid state means argon atoms are in a close packing. Argon atoms are in close packing, we can say. Argon atoms are in close packing. Argon atoms are in close packing. Close packing in the sense they are arranged very closely with each other. Sorry. Now this is one argon atom you will take, and this is one argon atom you will take. This is one argon atom you will take. Like this they are arranged. It is one argon atom. It is one argon atom. To the possible extent they are closely packed. Okay. Now between these two argon atoms, what type of attraction is there, that we will see between these two argon atoms. Okay, that means these two organ atoms are attracted with each other. That's why they are becoming solid. Attracted with each other by least force of attraction. That force is called least force of attraction, called vander Waals force of attraction. Vander Waals force of attraction. Vander Waals force of attraction, we can say. So between these two organ atoms, what is the force of attraction possible means one of the least force. That least force is called what means vander Waals force of attraction, we can say. Now, so between organ atoms, what is the force of attraction means vander Waals force of attraction. Here center point will take in this organ atom center point. In this organ atom center point will take. Now we will take this distance. In this distance we will take. In this distance, in that distance off we will take. That is called a vander Waals radius. That is called a vander Waals radius, you can say. That is called vander Waals radius. Okay. So what you have to do means, so we have to take organ in solid state. And in this solid state, organ atoms are in close packing. So these are organ atoms, they are closely packed. Between organ atoms, what is the force of attraction possible means vander Waals force of attraction possible. Now you have to consider center of nucleus here and center of nucleus here. Distance between them you have to take. That in that distance you have to take off. That off is called vander Waals radius. So now we will compare atomic radius and vander Waals radius. We will compare. Now how much is the vander Waals radius, that we will see. Here vander Waals radius is how much we will see. It is the center of nucleus. It is the half of the distance. This is called what means vander Waals radius. So how the vander Waals radius is there when compared with atomic radius, that we will see. Atomic radius in the sense center of nucleus to this outermost boundary. This is called atomic radius. This is called atomic radius. Now compare atomic radius and vander Waals radius. How it is there means atomic radius is less than vander Waals radius. So vander Waals radius is greater than atomic radius, like this is there. So now three types of radius are there. One is crystal radius, another one is covalent radius, another one is vander Waals radius. Depending on the requirement, we have to take particular radius. We have to take which radius we want to consider, that radius we can consider it. So now we have considered types of radius. We have considered how they are, how the magnitude is there. That also we have compared. atomic radius, van der Waals radius, crystal radius, and covalent radius. All these four we compared it. Sorry. Now we will see how the atomic radius changes in a group and in a period. How atomic radius changes in a group and how atomic radius changes in a period, that we want to see it. Okay, so now we will see the periodic trend of atomic radius in a group as well as in a uh, period, that we will see. So first we will see atomic radius, change of atomic radius in a group. We will see in a group how the atomic radius changes, that point we will see. So for that case, we will take first group, we will take, that means 1A group we will take. 1A group means alkali metals. Alkali metals are what means lithium, sodium, potassium, rubidium, cesium. Their atomic numbers you will see: lithium atomic number 3, add 8, sodium atomic number, add 8, potassium atomic number, add 18, rubidium atomic number, add 18, cesium atomic number. So we got atomic numbers of alkali metals we got. Then we will write electronic configuration. Lithium electronic configuration is 1s2 2s1. Sodium we will write sodium electronic configuration is 1s2 2s2 2s2. Then we will see 2p6 2p6 3s1. Like this it continues. Likewise 4 potassium in the sense 4s1, rubidium in the sense 5s1, and so on. Okay. Now we will see the radius of this down the group, how the radius is there, that we will see. Okay. So lithium, how many shells are there? Means 2 shells are there for lithium. 2 shells having electrons in the ground state. Sodium is having 3 shells having electrons in the ground state. So potassium in the sense 4 shells having electrons in the ground state. Therefore, down the group, what happens to the number of shells? What happens to the number of shells in the sense number of shells increases. Number of shells increases. Okay. So with respect to number of shells, how the radius will be there, that we will see. How the atomic radius will be there with respect to number of shells, that point we will see. Now lithium we will take. So for lithium, and nucleus we have written, this is 1s2, this 1s2, this is what means 2s1. Okay, 1s2 2s1 we have written for lithium. Next we will take sodium. Sodium we have taken. Sodium configuration is sodium nucleus we have written. This is what means 1s2. This 1s2. This is what means 2s2 2p6. This is what means 2s2 2p6. This is what means 3s1. This is what means 3s1. Okay. For sodium we have given. Now we will see with respect to number of shells, we will see the radius. With respect to number of shells, we will see the radius. Here center point we have taken. Here center point we will take, it is the radius. It is the radius for lithium. Now sodium we will see, here center point we are taking, here center point we are taking. This is the radius of sodium. This is the radius of sodium. With respect to number of shells, if you see how the radius is there, means like this. Okay, so as the number of shells increases, what happens? Radius increases. Radius increases. Okay, with respect to number of shells, we said atomic radius, we said. So what are the other factors? That affect atomic radius? That we'll see. Now, lithium atomic number is 3. Therefore, this nucleus contains 3 protons. For proton, relative charge is +1. So 3 protons means +3 we can say. Sodium atomic number is 11. So nucleus contains 11 protons. Nucleus contains 11 protons. So for lithium, nuclear charge 3 plus. For sodium, nuclear charge 11 plus. For sodium, nuclear charge is 11 plus. So potassium, nuclear charge is how much? 19 plus. Like this will be there. So down the group, what happens to the nuclear charge? Down the group, what happens to the nuclear charge in the sense nuclear charge increases. Lithium +3, sodium +11, like this. So nuclear charge increases means will it affect atomic radius or not? That we will see. Will it affect atomic radius? That point we will see. Now we will take lithium. Lithium nucleus we have written. Nucleus contains 3 protons and its 2 shells we have written. 1s2 and 2s1. That we have written. And sodium nucleus contains 11 protons. 1s2, 2s2, 2p6, 3s1. That we have written. 1s2, 2s2, 2p6, 3s1, that is for sodium. Now here we will see attraction. We will see now these 3 protons attracting 1s2 and 2s1. Here 3 plus attracts or pulls 1s2 and 2s1 in lithium. Here in sodium 11 protons pulls 1s2, 2s2, 2p6 and 3s1 and 3s1. Therefore, where pulling tendency is more, where pulling extent is more, in the sense in the 11 protons when compared to 3 protons. So due to higher attraction, what happens to the radius? Radius getting reduced. Okay, so here 11 protons are pulling the new electrons. Here 3 protons are pulling the electrons. Here more nuclear charge. Here nuclear charge is more when compared to this. So more attraction when compared to this. Therefore, what happens means radius decreases. Therefore, down the group nuclear charge increases. Therefore, radius decreases. Now we are saying radius with respect to nuclear charge only. Okay, it is not cumulative. This is not a experimental result. We are saying with respect to nuclear charge. We said, okay, so that it is not final conclusion. Sorry. Next, we will see another factor is what means screening effect. Okay, another factor is what means screening effect. So what is the screening effect that we will see? Now we will take lithium. Lithium nucleus contains 3 protons are there. Then we will take 1s2. 1s2 is the electronic configuration for lithium, and outermost shell is what means 2s1. It is the electronic configuration. This electronic configuration for what in the sense lithium we said. Now this electron is repelling this electron. This electron also repelling this electron. That means we can say 2s1 electron gets repulsion from 1s2 electrons. That means 2s1 electron gets screening from repulsion only called screening from 1s2 electrons. Therefore, 2s1 electron gets less attraction from nucleus due to 1s2. This less attraction is called, this effect is called what means screening effect. Therefore, if screening effect is high, then attraction with the nucleus is less. If screening effect is high, then attraction with the nucleus is less. That is the meaning. So screening means what? Repulsion. Repulsion only we are considering as screening. Due to repulsion, what happens means due to this repulsion, this electron goes somewhat far away. It is moving this side. It is moving far away. Therefore, distance between nucleus and this electron decreases. Therefore, attraction decreases. Okay. Therefore, from this we can say, as screening effect increases, then what happens means attraction with the nucleus, attraction between nucleus and electron cloud, decreases. Therefore, what happens to the radius? Means radius increases. We have to say radius increases. So screening effect increases means attraction between nucleus and electron cloud decreases. Therefore, radius increases. We can say. So down the group, what happens to the screening effect by outermost electron, that we will see. Now lithium configuration is 1s2 2s1. Sodium configuration is 1s2 2s2 2p6 3s1. So here outermost shell is 2s1. So 2s1 gets repulsion from 1s2. Okay. So 2s1 gets screening from 1s2. Therefore 2s1 gets less attraction from nucleus due to 1s2. Okay. Therefore 1s2 shows screening effect over 2s1. 1s2 shows 1s2 shows screening effect. 1s2 shows screening effect over 2s1. 1s2 shows screening effect over 2s1. Set. What about in sodium? In sodium, outermost shell is 3s1. 3s1 gets repulsion from 1s2, 2s2, 2p6. So 3s1 gets screening from 1s2, 2s2, 2p6. So 3s1 gets less attraction from the nucleus due to 1s2, 2s2, 2p6. Therefore we can say 1s2, 2s2, 2p6 shows screening effect over 3s1 Therefore which will get a higher screening effect, that we can say. So lithium gets a lower screening effect, whereas sodium gets a higher screening effect. So down the group, what happens to the screening effect? You see, lithium gets a lower screening effect, sodium gets a higher screening effect. So down the group, screening effect, what happens? Increases. So down the group, what happens to the screening effect means increases. So down the group, so we can say down the group, screening effect increases. Therefore, attraction between nucleus and electron cloud decreases. Therefore, radius increases. So far, what are the things we have discussed that we will see? So down the group, one point we said number of shells. Number of shells we said increases. Therefore, radius. Therefore, radius, what we said in the sense increases, we said. So radius increases, we said. Next, we said nuclear charge. Nuclear charge increases. Therefore, radius decreases, we said. Next, we said screening effect. Screening effect increases. Screening effect increases. Therefore, radius increases. These are the points we said. So, next, we have to see these points we said. Okay. What is the experimental result says? Before seeing experimental result, another factor we have to see. What is the another factor in the sense effective nuclear charge? Another factor is what means effective nuclear charge. Effective nuclear charge. Effective nuclear charge, the symbolic representation is like this. It is equal to what means nuclear charge minus screening constant minus screening constant. Screening constant is from this screening effect. Screening constant is from screening effect. Screening constant we have to calculate using what means Slater rules. Using Slater rules, we can calculate screening constant that is from the screening effect. So we will calculate a screening constant that is called sigma, and the nuclear charge Z. Z minus sigma is called the effective nuclear charge. So this effective nuclear charge is nothing but a cumulative effect of this nuclear charge and the screening effect. This nuclear charge and screening effect, cumulative effect is called effective nuclear charge. That the effective nuclear charge we have to consider it. So we will consider effective nuclear charge, we will consider, and number of shells we will consider. Then we will say the radius. So what experiment says, that we will see. Experiment says radius is how much, that we will see. Now first group we will take. So first group, lithium. For lithium, radius is how much in the sense 1.23 angstrom. That is what we are taking in the sense covalent radius we are taking. So lithium is a metal. Then how to find covalent radius? Lithium is a metal. So we have to say metallic radius. Then how do you say covalent radius for this? That means you may ask this. Lithium forms compounds. In the compounds, lithium is having covalent nature. Lithium compounds are having covalent nature. So we got covalent radius. Sorry, okay. Sorry. So for alkali metals also we can say covalent radius. That point we came to know it. Sorry. Next we will see lithium crystal radius. We will see. So crystal radius for lithium is how much, means 1.52 angstrom. Sodium is 1.86 angstrom. Then potassium 2.31 angstrom. Then rubidium 2.44 angstrom, 2.44 angstrom. Then cesium 2.62 angstrom. Then francium is radioactive, so we have not said any value. Then we will see covalent radius for this. Covalent radius we will see. Covalent radius. Lithium 1.23 angstrom, sodium 1.57 angstrom. Next, so this potassium 2.03 angstrom, rubidium 2.16 angstrom. Then cesium 2.35 angstrom. Now you see that atomic radius, crystal radius and covalent radius, you see crystal radius is greater than covalent radius in each case. In each case, crystal radius is greater than covalent radius. Okay, sir. Now down the group, what happens to the radius that we will see? Now crystal radius you will see here rising, 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 rising. Covalent radius we will see rising, 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 rising. So what is the cumulative effect? The cumulative effect says that the experiment says that down the group atomic radius, generally atomic radius increases. Okay, down the group, what happens to the atomic radius means that is increasing. It is the experimental result. It is the experimental result. So how to explain this experimental result, that we have to see. So experimental result says down the group atomic radius increases. Either you can see in the form of crystal radius, you can see, or in the form of covalent radius, you see. In whatever the form you take, down the group atomic radius increases, we can say. It is experimental result. How to explain this experimental result, that we want to see. Okay, so to explain this experimental result, now we will take one factor called number of shells. Number of shells increases down the group, therefore number of shells increases. It is one of the reason. Another reason what we have to take, in the sense effective nuclear charge we have to take. Effective nuclear charge is equal to nuclear charge minus screening constant. Nuclear charge, this is nuclear charge that we have to substitute here. And this is screening effect. That screening effect, from the screening effect we have to calculate screening constant using Slater rules, that we are substituting here. So Z minus sigma is called effective nuclear charge. Okay, this effective nuclear charge, what happens down the group? Effective nuclear charge down the group, what happens? That we'll see. Down the group, effective nuclear charge increases. Effective nuclear charge increases in the sense which is dominating, nuclear charge or screening constant, out of these two. So nuclear charge means this one. This is screening constant is from screening effect. Down the group nuclear charge increases, screening effect also increases. So down the group what happens to the nuclear charge means increases. Down the group what happens to the screening effect means increases. So screening constant also increases. Now if you substitute these two values are known. If you substitute these two values, you will get effective nuclear charge. How effective nuclear charge is there down the group means effective nuclear charge increases. That means out of these two, which is dominating, Z or sigma? Z is dominating when compared to sigma. Therefore, effective nuclear charge increases. Effective nuclear charge increases means radius should decrease. Radius should decrease. Okay. Effective nuclear charge is nothing but Z minus sigma. Z is dominating when compared to sigma. That's why effective nuclear charge increases. Therefore, effective nuclear charge increases means radius decreases. It is explanation. Using effective nuclear charge, we can say radius like this. Using number of shells, we can say like this. Now, what is experiment? Experimental fact says down the group radius increases. It is experimental fact. Now, to explain this experimental fact, what is the suitable reasoning? What is the suitable reasoning in the sense to explain this experimental fact? The suitable reasoning is this one, but not this. Because experimental result says down the group atomic radius increases. So this reason explains that. This reason is not explaining that. Therefore, down the group number of shells increases. Therefore, atomic radius increases. It is the explanation. Experimental fact says down the group atomic radius increases. What is the explanation? Down the group number of shells